even nicer to see this. I would welcome you, everybody, all members of the Association ProISSI, our friends, to this. I'm very pleased to see so many of you. That's great. Tonight we have Professor Dr. Michael R. Meyer is our guest for tonight, our speaker. Michael did his PhD from the University of Massachusetts. He was then moved to the Max Planck Institute in Hamburg, where I was also for a long time. Then he was
much after me.
That's true. He was then a Hubble Fellow, very prestigious, of course. Then he became the professor at Stewart Observatory at the University of Arizona. Then he was a professor at ETH Zurich, actually, until 2016. So he's very rich. He then moved back to the United States, University of Michigan in Ann Arbor, where he's a professor and chair of astronomy. Now he's also, of course, the Johannes Geis Fellow of ISSI at the moment. Therefore, we're very pleased that this year we could continue this tradition that one of the speakers of ProISSI is also the Johannes Geis Fellow. Yes. It's great to have you here. Before I give you the word, I would like to invite everybody who enjoys this kind of presentations, but who is not yet a member of the association, to go to our website, to register. It's really not very expensive. It's 50 francs. I think you also get a very nice apéro. Actually, I would claim that for 50 Swiss francs, you pay less for the food if you go to So, with that, Michael, please, you have the floor.
Thank you, Christoph. Sehr geehrte Damen und Herren, grüezi miteinander. Leider ist mein Deutsch nicht gut genug für solche Vortrag, aber dann muss ich auf Englisch sprechen. It's a very great pleasure to be here today, and I've enjoyed already all the events of this week, which are very exciting for many institutions. Tonight, I want to tell you a story about our origins as life forms in our galaxy and in our universe. And the story that I want to tell was made possible by the James Webb Space Telescope. Some of you in the audience will have heard Thomas Surbuchen speak earlier today about the search for life at NASA in a larger context, although he did highlight some aspects of the James Webb Space Telescope. But I'm going to tell you my version of that story and go into some details about work that I was involved in early in my career, and most recently with the data that we've gotten from James Webb. I have two goals tonight. One is to inspire you, maybe three goals. Also to teach you something. I hope you come away learning something, and I think I should also entertain you. So hopefully I can at least meet two of the three goals. You never can get all of the three. So let me begin. This is an image made famous by Carl Sagan. It is an image of the Voyager spacecraft looking back towards the Earth. And this little, what he referred to as the pale blue dot, has everyone you've ever known, everything that you could ever conceive of as a human being is on that little point. And he referred to it as a blue dot in pale sunbeams. And that's because this is not a great scientific image. These are not the rings of Saturn. This is scattered sunlight off of a piece of the apparatus of the satellite. But it is a beautiful image, and it does remind us that we all come from star stuff, and we all are on this little point of light. So, the discussion topic today is origins, and this is a theme that at least NASA has embraced for many, many decades. It really formed the backbone going back to the early 90s, if not the late 80s, on how NASA decided what kinds of exploration and science to conduct. And ultimately, we want to know where we came from. We want to know our place in the cosmos. And of course, the topic everybody would like to know an answer to, are we alone as life forms in the universe? This covers these three questions all the way back from the Big Bang in the beginning of the universe, its structure and evolution, and where we will end up many billions of years from now, but also this complex mystery of the biochemical origins of life. Life itself is, I think of it as kind of a twin miracle. You need a metabolism, some kind of way of extracting energy from your environment, a chemical network. You also need a way to reproduce. You need to collect your genetic material, you need to pass things down to the next generation, and hopefully the good things make us stronger and better, and the weaker things will not persist. And then you need to take these two miracles, and you need to wrap them in a membrane, so that the life can exist and go on. And we think of this as being a planetary phenomenon. You could imagine the diffuseness of space. How could you bring the right chemicals together? You imagine a world and a surface with gravity. Okay, maybe I can collect things. But then further, if you immerse the world completely in an ocean, that's too big of a bath to collect the chemicals that you need. So you must then imagine some land, and maybe even a discontinuity between the land and the sea, which provides opportunity for small pools, things to move around, disequilibria to collect. And we think that that might be the place where life might have come from. And so part of what the James Webb Space Telescope can do is to help us explore these origins. But I'm also going to tell you a short story about the origins of the James Webb Space Telescope. Our host this evening, Antonella Lanota, knows well the great triumph of the Hubble Space Telescope, going back to its launch. Of course, it needed some corrective glasses. If you don't know that story, that's a very interesting one to tell. But with the help of astronauts, those corrective glasses were placed, and the images from Hubble are extraordinary. They taught us about many things about our place in the universe, and indeed the origins of stars and planets. But even in the early 90s, the question came already, what is next? Hubble was conceived in the 1960s. It took 30 years. What about the next thing after Hubble? And it was already recognized that that would probably have certain characteristics, which I'll talk about in a minute, but the central one was being a mostly infrared telescope. Hubble just touches the infrared, and James Webb goes farther. This is an image from Hubble of the so-called pillars of creation in the Eagle Nebula. And in these dark fingers are clouds of gas and dust in space, which you can imagine might form stars. The reason we can't see through the fingers is that the dust scatters the light out of the way and absorbs some of it too, and so we cannot see through, like you might have a view of through smoke over a neighboring house. You can't see through the smoke as well. But when you go into the infrared, the universe becomes visible again. The longer wavelengths of light are scattered less efficiently than the shorter wavelengths, and so we're able to see through in the infrared. So we can get through the dust and find the stars and planets as they're forming. So we've already established that we might want to go into the infrared. There were other missions that preceded the James Webb, some based in Europe and some in the United States. The Spitzer Space Telescope was a real pioneer in cold telescopes in space, but there was before also the Infrared Space Observatory by the European Space Agency and the Herschel Observatory as well. And both of these made important strides before we got to the James Webb Space Telescope. This is the electromagnetic spectrum going from high frequency or short wavelengths to the longest wavelengths. And the longer on this side you go, the easier it is to penetrate through that dust that I mentioned. This penetration, first of all, the infrared allows you to see cool objects, no pun of the word in English, cool, but temperature, things that are colder. Their Planck functions emit at farther and farther infrared wavelengths based on their temperature. So hotter things will be seen more at short wavelengths, and cooler things seen better at long wavelengths. I mentioned already the dust that you can see in star-forming clouds. This is an image of a protoplanet seen in formation in the infrared. Again, being able to see through the dust and gas of a swirling disk around a young star forming, and that planet is forming itself within that disk. And finally, the other aspect of the infrared, and this was really what drove the origins of the James Webb Space Telescope, was the expansion of the universe and the redshift of light. As the wavelengths are stretched out through their travel, you see back in time, when you can look farther into the infrared, to light that was emitted so long ago in the early universe. And so Hubble was kind of stuck with how far back in time it could look, and James Webb provided a whole new set of windows that just kept opening back in time to what we refer to as high redshift, as the light is shifted into the infrared. And really one of the goals of the James Webb was to see the first stars and cores of galaxies, the so-called active galactic nuclei, or black holes that might have illuminated the universe for the very first time. And that was really what drove its early evolution. But there was more. This is an image of what was then called the Next Generation Space Telescope, the science working group. You can't see it, but I'm back in the very back there as a young person, a much younger and lower mass version of me is seen in these photographs. I had the good fortune after my time in Heidelberg to be appointed to this commission that helped sketch out what the instruments for James Webb would be. And it was 3 years, and it was a very exciting time when I was a postdoctoral fellow. And it was exciting to think about what else could James Webb do. And in fact, it was very easy to convince this committee that it should go all the way into the mid-infrared. The argument practically made itself, and it's really illustrated in this figure. What is being shown is basically the brightness of the sky in some units of surface brightness, bright per unit area, as a function of wavelength. And this is what we suffer on the ground, because everything in this room is emitting at the peak wavelength of the Planck function of 300 Kelvin, namely 10 microns. And that's where the mid-infrared is, where we want to find planets like Earth. We are all glowing and making noise for the telescopes to try to do that. It's 6 orders of magnitude worse from the ground than it is in space. And it turns out to be the square root of that number that defines the noise that we must fight against. So you do much better by going into the space-based background. Furthermore, there are windows that are not accessible to us because the Earth's atmosphere and the molecules within it. Again, these are molecules on our planet we want to study in other planets, and all of that light is blocked by those molecules. So we can only see, this is the transmission, and so if there's nothing, this is the blue parts are the parts we can see, and the white only we cannot see through. So they're important molecules that we can't access, water, carbon dioxide, others, that we can't simply see from the ground. So we really do need to go in space. And JWST in space has incredible sensitivity, it has enormous wavelength coverage, and it has field of view, which is how big the pictures can be. There are technical reasons, I can go into that, why that's challenging from the ground, but those were the 3 things that defined what we wanted to do going forward. So, here is an artist's rendering of the James Webb Space Telescope. This was a collaboration, an international collaboration between NASA and ISSI and the Canadian Space Agency, and it always was, from the very first day. We would join forces, join arms together, and march up to the Lagrange point 2 with JWST and make this beautiful instrument that could do these wonderful things. I was going to show the launch, but it's about 1.5 minutes. Thomas already showed it earlier today. The link is on YouTube, and you can watch it. It's very inspiring, and I encourage you to do so. But because there are other parts of my story I want to tell, I'm going to skip that for you today. So, some facts about the Webb telescope. First of all, it is very far away from us right now. It had to go 1 million miles all the way to the other side of the moon, if you will. And it's orbiting this Lagrange point between the Earth and the Sun. And it's an unstable equilibrium, so it needs just a tiny bit of fuel to make course corrections. So there's an expendable, but it's not much that it takes, and it has way more fuel than it really needed. So we think the lifetime of the mission will go on certainly more than a decade, maybe even close to 2. We shall see. The wavelengths I'll touch upon more in a minute. It is an infrared telescope. I was trained as a student as an infrared astronomer, so this is my theme. The mirror size. There's a person for scale, 1.8 meters. This is the Hubble Space Telescope. Again, not a small thing, but a wonderful, incredibly productive. It's the yardstick by which all other scientific facilities are measured in terms of productivity. And here is the James Webb at 6.5 meters in diameter, considerably larger than the Hubble Space Telescope. Very exciting new capability for us. For fun, here are some of the engineering aspects of the back end. So there's a cold side and a hot side. And there are 5 layers that are between the sunlight and the telescope itself. You may remember your Oma telling you to put layers on when you go up into the mountains. That's because your heat is coming off of you. It's heading in equilibrium on this layer. Half of that energy goes out and back in, and so on. And so you have an insulation. That's exactly what these 5 layers are doing, protecting the telescope from the sun. So it has 5 of these enormous sun shields that are protecting the telescope. The light reflects off of the telescope back to this mirror in the middle, and then back through this tiny hole and into the other side where all the instruments sit, and where we make our measurements with cameras to take pictures and spectrographs that break the light up into its constituent frequencies so we can analyze in finer detail the spectra of different objects. It's quite cold on the back and a bit hotter on the front. That is its own engineering challenge to make sure that the heat transfer is minimized and that the things that are hot can operate hot and the things that are cold operate properly cold. This is a bit sad. This is a picture of the last one we have. It looks like a beautiful jewel box. It was, a little bit after Christmas, but this is the last picture we have from the deployment of JWST, and off it goes. There's another movie which takes about 12 minutes to show that I also don't want to take time to show you, but if you can find it on the link I show you at the end, I encourage you. It is the unfurling. That night, it was Christmas, as Thomas alluded to earlier, in 2001. I was traveling back with my family to visit my mother and the extended family. We were in a hotel, and I could not get Wi-Fi in this hotel. It was in the middle of the pandemic. It was a new staff. They didn't know how to create Wi-Fi in their building. And I simply woke up at 4 a.m. and I didn't see it. I didn't see it. It was really terrible. I'm part of 2 of the instrument teams. Working on it since I left that planning group, and I've been working on it since 1997 was when I started working on JWST. So anyway, it left and started that process of unfolding. And we remember when the Mars rover landed, they spoke of the 7 minutes of terror, as all these terrible things could have happened. This was 40 days of terror. There were hundreds of movements that had to go, and several of them were single-point failures. And it is a marvel of engineering that it works. I still pinch myself that I'm not dreaming. It is incredible that the thing works as well as it does. So, the instruments, there are 4 to speak of. Separated into wavelengths, we have the visible. So this tiny part of the spectrum that we can see with our human eyes, shown all the way far on the right. Then the near infrared, that's 1 to 5 microns, where we have the camera that was built at the University of Arizona, of which I was a part, and nearest, which was built through a collaboration led by the University of Montreal in Canada, which I was a part. Near spec built entirely in Europe. And then the mid-infrared wavelengths from 5 all the way out to 25 microns or so, that was MIRI, and that was a joint US and European collaboration to build that camera. Miri looks like it's the big thing here because it takes up so many wavelengths. But much of the astrophysics, although Miri is very important, the shorter waves are indeed the heart of the observatory and get most of the use. But Miri is very, very powerful as well. Okay. Now I want to launch into some of the science that we've been able to accomplish in the last couple of years. But first I want to do a little bit of a background. A lot of what I'm going to talk about will be stars and their formation, planets and their formation, and planets from Jupiter, a gas giant planet, all the way down to planets like Earth, which we refer to as a terrestrial or rocky planet. What is the difference between a star and a not a star, something that is not a star? And the main difference is the ability to fuse hydrogen into helium in its core as an energy driver, an engine that makes the star shine for hundreds of millions or billions of years. That's the difference between a star and not a star. But once you pass into the not a star category, we refer to a continuum of objects as brown dwarfs, or so-called failed stars. This term was coined and studied in the late 50s, early 60s at the University of Michigan, as it turns out, by Kumar. But the difference between a brown dwarf and a planet is not so clear. And in fact, I will argue that there's a huge overlap between what could form like a planet and what could form like a brown dwarf. And we need to do more work to really understand the subtleties between that difference. Finally, Earth is about 300 times smaller in mass than a planet like Jupiter. And this boundary between brown dwarf and star is about 100 Earth masses. Sorry, 1,000 Earth masses. Okay. So, how do we form stars and planets? Well, there's a kind of an argument for planets, at least, whether they form top-down or bottom-up. Top-down is a style where you really just have a pile of gas, and you have to ask yourself whether the gas will collapse or expand out. And that's a competition between gravity pulling things in and internal pressure created by high temperature, which wants to push things out. If the gravity is stronger than the temperature inside, it will collapse. That means if this ball of gas can cool through lines of atoms or molecules, it is more likely to collapse. And that's in fact how we think stars form. And in the disks of gas and dust around young forming stars, there are similar processes that go on that could form a planet or a brown dwarf companion from this collapse, that gravity locally will overwhelm the internal pressure inside a ball of gas. But there's another process that can happen in circumstellar disks where dust, when it collides with another dust particle, can stick. And then those two particles could stick to two more, and the things can grow up, and then a series of processes are initiated where the things can get larger and larger over time. It's not unlike the growth of these things underneath your bed or cupboard. Yeah? Staub. This is how planets can form.
I don't have that.
Well, then you should come and clean our place. So these processes, either one can happen, and we really want to understand what makes a brown dwarf versus what makes a planet. Okay, well, one way we can trace the temperatures inside these clouds is by doing spectroscopy. This is a picture of the so-called Kirchhoff's laws, where if you have a light source and it shines through a cloud of cooler gas, you can get absorption features. And those absorption features are like fingerprints. They're unique to each element or molecule, and you can find out the composition by matching up these lines through the laws of quantum mechanics to what those absorption features are. You can also just have a continuous spectrum of the Planck radiation from a body of a given temperature, or you can look at the gas without a background source, and these lines that get absorbed eventually will de-excite and emit. And so you'll see a complementary set of emission lines where there can be absorption lines. I explain this because one of the unique experiments we are trying to do with James Webb is to use background starlight shining through clouds in the infrared to get at the composition of the gas and dust. And really what we're looking for is what the dust composition is in terms of silicon and carbon. These are two key elements, and in fact carbon is a key element in the origin of life. Believe it or not, as astronomers, I'm embarrassed to tell you, we still do not know what is the major carrier of solid carbon in the gas and dust between the stars. And we know our Earth is incredibly underabundant in carbon, believe it or not, compared to the interstellar medium. So we want to know what that stuff is, and when it comes into this disk of gas and dust to form planets, where does it go? How do we burn it? How do we do alchemy of transmuting the carbon into some other form that can leave us? That's the mystery we try to solve. So we study young clouds like this, which look, this one has no star in it. All those dots are behind and shining through. This one is just on the edge of starting to infall because the temperature reached low enough relative to its gravity, it has initiated collapse. And there's one more that I haven't shown you, which has a real star forming in it in the next slide. By looking at this background absorptions, we can look for ice features of different, at different wavelengths and try to trace the nature of the ices, water ice, carbon-rich ice, carbon dioxide ice, and really try to understand where the carbon is sequestered in these dark clouds. Well, this was the unexpected picture we got of this one, B335, that we know is forming a protostar. But when we look at it with Webb, we see these cones, these jets of material shooting out from the system. It's a bipolar nebula, and there are even jets that are seen out here to form little bow shocks at different places. Some of the energy of collapse is somehow transformed into a jet that shoots out from the poles. This helps it lose angular momentum because it's not just an energy argument from gravity in and pressure out. There's also rotation in the system, and we have to conserve angular momentum. So if we want that cloud to collapse and it's spinning a little bit, we need a sink. We need a source to remove the angular momentum, and we believe these jets do that. In this particular system, we're able to measure the velocities of these little parts of the jet coming out, and we even have evidence that there's a binary star, not a single protostar, but a binary forming in the center there. So it's been much richer and complicated than we thought it would be. But the images from Webb are astonishing. I should have mentioned, what on earth are these crazy white streaks across the image? This is the diffraction of the supports of the secondary mirror and the way that the light propagates through the system. It's a natural part of any telescope that you can't get rid of, but there are very clever ways we can minimize it so that it doesn't affect our images. But every bright star here has this pattern, this characteristic pattern of diffraction caused by the solid structures that support the secondary mirror. Okay, well, stars don't just form in isolation. Sometimes they're multiple stars, and sometimes they form in clusters. Groups of stars, dozens to thousands of stars, forming together in one giant entity we call a molecular cloud. It turns out most stars form in groups. It seems that nature abhors isolation. It likes to form things together. And one of the amazing discoveries of James Webb, which was just reported last month, again by our host, Antonella Lanata and her collaborators, was evidence for brown dwarfs, these failed stars, in another galaxy, a neighbor to our own, the small Magellanic Cloud. If these observations are confirmed, and I have no doubt that they will be, it will be fascinating to compare these brown dwarfs to the ones in our own galaxy. So this brown dwarf is supposed to be spying the Milky Way here from afar, and this is just an imagination of a zoom-in of a spot where there's a star cluster in the Milky Way. The composition of the gas in this neighborhood galaxy is very different from our own, and that will help us understand the formation processes. In astronomy, we don't do laboratory science. You probably know this. It's an observational science. So for experimental design, we're always looking for some kind of way of changing conditions, a knob we can turn like we would be in a laboratory. And here it's composition, or amount of heavy elements in the gas, from this region to the ones we study. This is the study that we were involved with from the nearest team. It's a star cluster called NGC 1333, and we tried to find these brown dwarfs in a novel way by putting in a prism, the kind of thing you can hold to the sun and make a rainbow in your kitchen. We put that in the way of our camera, and it gave us a spectrum of every single object in the field. Turns out, for technical reasons, it's not the most sensitive way to do such an experiment, but it gives you the full field of view and a spectrum of every point. And we found 6 brown dwarfs in this cluster, all the way down to about 3 times the mass of Jupiter. Very, very tiny things. And in this process of forming stars and brown dwarfs, there's something called the opacity limit of fragmentation. It's a real end of the mass of things that can form in isolation in clouds of gas and dust in space. And we are all on the hunt for that with the James Webb. This beautiful image is showing you a lot of emission lines as well as scattered light in the blue from nearby bright stars. And this was a study led by a student, a postdoc at Johns Hopkins, and the link for the press release is shown here, as well as for the work that was highlighted in the ISSI press release shown above. So this is one star cluster. Another star cluster, this is called the Flame Nebula. If any of you are amateur astronomers in Orion, you would be familiar with the flame. And when you look at pictures of it taken at visible wavelengths with our eyes, this is completely void of anything because it has a giant dark dust lane right in the middle, blocking all of the stars. I wrote a program for this star cluster in 1998, which was part of the design reference mission for what became James Webb. And I cannot tell you how gratifying it was 25 years later to have my student analyze these data, and of course did a way better job than I ever would, because younger people are smarter and more talented than I am as a professor. In this star cluster, we have seen many brown dwarfs, but we have also seen a turnover in their frequency. Below about 10 times the mass of Jupiter, there are considerably fewer of these brown dwarfs, and not a single one below 2 Jupiter masses, similar to the 3 Jupiter mass limit in the other cluster. And it smells like somewhere we have found this limit for brown dwarf formation. This is something called a color magnitude or a Hertzsprung-Russell diagram. On this axis is how bright the object is. So down here is faint. And this is an axis of a color which measures relative temperature. So that's the thermometer shown here. So if something is faint and cold, it's over here. This is the collection of the objects we found, and this is where Jupiter would appear if it were shown through many, many, many layers of dust. It would appear over here. And these are the objects we found. Different amounts of dust. Each line represents a different mass. And this is 1 times Jupiter's mass, 2 and 3 times Jupiter's mass. So we really think we found the turnover in what astronomers refer to as the initial mass function, and maybe this opacity limit of fragmentation in the interstellar medium. The paper's been submitted, and we have time coming up in the next few months to take spectra of all these little dots to see more carefully what their temperatures are, rather than just looking at how red or blue they are. We'll actually have a spectrum, so we can look at those fingerprints of different molecules in the atmosphere. Okay, now I want to zoom in on a single object, a single star that is forming like the sun, very young, just a few million years old, and surrounded by a disk of circumstellar gas and dust. This is one such object. I don't know if you can see, but there are spiral arms in this disk, which suggests that the disk is very massive and may be capable of forming planets like Jupiter from a top-down collapse scenario. One of my other former students from the ETH, Andrea Banzati, has led a team studying the molecular emission, not resolving spatially the disk, but looking at the gases inside of that gas disk. What are they made of? And he's been trying to confirm a hypothesis we had 10 years ago, that these are very water-rich disks. There's an idea or a theory about how such planets could form, where icy materials would migrate close to the star and then melt, and then make very watery stuff inside, where planets could form and gather that water. And this is part of a story, we think, about how Earth would form and has water oceans like our own. But Gabriele Cugno from the Ticino, he was a student here in Zurich and then came to work with me for 2 years in Michigan. He was studying this, and it was part of our guaranteed time from the NIRCam team, and he found a little dot. So here's the star. We've blocked this out because the data are poor because of how bright the star is. And there's a tiny little smudge there. It doesn't look impressive compared to all these other smudges, but what he has demonstrated is that having a smudge here and then a negative on one side and a negative of another is a real key that it's a real source. And the reason for that is we use a technique called angular differential imaging, where we take an image at two different orientations of the image and subtract them from each other. So we naturally get a little bit of subtraction on either side. And if this object is real, it's below a Jupiter mass, and it's about 200 times the mean distance between the Earth and the Sun. So it's very, very far out in its possible solar system. And we have time to follow that up and see if it is a real companion. The chances are very high that it is, but we haven't proven that yet. There are a dozen programs like that many of us are trying to find protoplanets forming in gas and dust-rich disks around stars like the Sun at very young ages. Okay, I've only got a few more slides here, and then I'll let us all rest and have questions if you have some. When we find a wide orbit companion, so this is a different one, but it's a similar kind of situation, a star like the Sun, a planet about 10 times, or an object I should say, about 10 times the mass of Jupiter, and it's more than 200 times the mean Earth-Sun distance away. So it's a very unusual planet if it is a planet. And you might ask yourself, what are these objects at young ages, and how do they compare to planets like our own Jupiter, which itself is very cold now after billions of years of cooling? And if you think about it, it's really just like a fire cooling overnight in a campsite. The embers are cooling at a rate determined by their current temperature. And when it's really hot, they cool fast. And as they get colder, they cool a little slower and a little slower and a little slower. And that difference in cooling rates as a function of time, you can make an integral and calculate the time it takes for something to cool from this temperature all the way down to this temperature. And this is what we do in these models of these failed stars that don't have their own energy source. Stars burn hydrogen into helium and shine for a long time. These objects just cool down and fade away. So if an object at about 50 million years has a temperature of 1800 in units of Kelvin, just an offset of 270 from the Celsius scale, after 1 billion years it would cool to the temperature of 300 kelvins, and then after about 5 billion years it would cool to 175. Well, that's about the temperature of our Jupiter. It's 130 Kelvin, so I'm doing this analytically on a chalkboard. It's not a detailed calculation, but I get about the right order of magnitude. So these objects form and cool in this way, and we can trace that by taking spectra of them. Furthermore, when we get the spectra, we can try to see their composition, and we can try to understand if they formed like a star of clouds of gas and dust in space, or like our own Jupiter. Our own Jupiter is enriched in heavy elements like carbon, nitrogen, and oxygen by factors of 3. There's just a lot of extra volatile material put into the atmosphere of our Jupiter, and it looks very different than it would if it had the same composition as the Sun. These are spectra that we've obtained with James Webb Space Telescope. The name of the planetary mass companion doesn't really matter. But we and 2 other groups have collected just the first few of these objects. So you can just look at the patterns and try to compare them to each other. This is the first one that we did as a community in early release science. And it has these nice molecular absorption features. This is not noise, by the way. This is very, very high signal-to-noise data. So each of the wiggles you see is not nonsense. They're actually individual lines in the spectrum of that object, so we can do pretty detailed analysis. The next one we looked at was this one, the blue one here, and you'll notice it looks very funny over here. And we've determined that they're similar in principle, but this little thing, about 10 times the mass of Jupiter, is surrounded by its own disk of gas and dust. And so it has what we would call a circumplanetary disk. We think our own Jupiter had such a thing, and that the Galilean satellites that Galileo first observed through the first telescope, that was probably formed in one of these circumplanetary disks. So it's kind of planets all the way down, if you want to think of it this way. And this is the one that Per Karlsendorf, a Swedish postdoc in my group, has obtained, and it is shockingly similar to the first one. So no disk around it of gas and dust, but we're trying to analyze its temperature and its composition. We zoomed in on a tiny piece down here just to show you what the opacity or the lines of carbon monoxide look like in green. And if you squint, you can see all of these lines reproduced in the spectrum. So we know it has carbon monoxide. We just need to measure its relative abundance to the other chemicals in its atmosphere and try to figure out if it's enhanced in carbon, nitrogen, and oxygen or not. Well, there's another way to study planets, and that is something that the colleagues here in Switzerland have really led. Of course, the revolution of planets around other stars was started here in Geneva in 1995, led to the Nobel Prize for Michel Meyer and Didier Queloz just in 2019. And those kinds of objects that were found very, very close to their host stars allow us to probe them in different ways than the images that we take, pictures of the planets. This is a different way of studying hotter stars, and it's been a revolution how much information we can pull out of these kinds of systems. However, they're not like our own. This is a kind of Jupiter or Neptune planet that is inside the orbit of Mercury, orbiting its own star. So it's a very, very different to the planets we have in our solar system. When a planet crosses in front of the surface of the star, it dims the light of the star. And that's shown here, maybe in white. And if you look at a different wavelength, the planet can have an effective different radius. So say in the red, it's a little bit bigger. And then you can observe another dip, which is a bigger dip. And then the planet can appear to have a radius that's even bigger still in the blue. And it has an even bigger dip. When you make observations like that at different frequencies, you can then put together a spectrum of the absorptions of the planet. And the idea is that the radius appears bigger because you're probing lots of gases higher up in the atmosphere. That's why the dimming changes with wavelength, and we can invert that to make a spectrum. Here is such a spectrum. Now, these are not as beautiful high signal to noise as the other ones I showed you, but it's very clear that there are these features of water vapor shown here. And the analysis of that data done by Ryan McDonald, who is a Hubble Fellow in my group at Michigan, and an undergraduate, a bachelor's student, Ishan Raoul. And this work was led by a graduate student, Caroline, at the University of Montreal, the home of the nearest building team. This world that they have found appears to have such a strong steam atmosphere that it must be surrounded by a global ocean, many, many kilometers thick. That's fascinating and interesting to learn. But I believe these water worlds are probably not habitable because they lack the surface land I mentioned at the beginning as being a discontinuity or a place for disequilibrium to occur that might lead to life. It turns out the models that my colleagues here in Bern make for planet formation primarily form water worlds like this. And it may be that the formation of these Jupiters in these disks can stop the water from coming in and making these water-rich planets. So it's not only that we want to study Jupiters because they're fascinating and Earths because they might have life. It turns out the relationship between having both a Jupiter and an Earth could be key to having a life-bearing world. And this is the main focus of my research going forward, is to disentangle that possible connection. Well, we are studying planets, we are studying these failed brown dwarfs. We have done a survey of these brown dwarfs, and we in fact found a binary, a very close companion of two of these little brown dwarfs together. They have a funny name called Y dwarfs. Why, I can explain to you later, but it's what they are called. And it turns out that this one object we found is a double. Here's an artist's conception of it. I mention this just because it's a kind of a remarkable edge case or end member of the formation process, and it kind of straddles the boundary of stars or brown dwarfs and planets. The primary is 10 times the mass of Jupiter. its companion is 5 times the mass of Jupiter. And they are locked in a gravitational dance. They're billions of years old. One is about 300 Kelvin, the temperature of the Earth. One is about 200 Kelvin, much cooler. And the separation between them, curiously, is 1 astronomical unit, or the mean distance between the Earth and the Sun. So it's just kind of a funny example of how planet formation and star formation might be parts of the same thing when studied in detail. James Webb has this enormous sensitivity, and it will eventually, we will unlock, this is a plot, I should say, of planet mass in Jupiter masses. So 1 Jupiter is here, and this is the distance from the host star. So Jupiter, again, is here at a few AU. We have our own Earth, shown here, Venus, and so on. This is the system of planets. We are not complete on this side of where the stick is right now. We haven't been able to see most planetary systems like our own, and this is the whole range of discoveries we've made in the last 25 years. James Webb Space Telescope will push down so that at large orbital distances, maybe 10 or 100 times the Earth-Sun distance, we'll be able to see planets like Venus and Neptune in our own system around these other stars. And that's a very exciting parameter space open up. Okay, well, James Webb is fantastic. I hope I have convinced you of this. But it's not the only thing, and there are many ways that these different kinds of telescopes can be extremely complementary. On Wikipedia, a place where most scientists go to get their information, there's a lovely graphic of all the big telescopes in the world. And I love to stare at this picture. It has, if you play tennis, you can see a tennis court here, or perhaps basketball. There's this one there. And being here in Europe, and Switzerland being a member of the European Southern Observatory, we are very blessed and grateful that this thing exists now and will be available soon. It's called the Extremely Large Telescope. It has a diameter of 39 meters across. Can you imagine? I can't wait to go there and see it with my own eyes. It's planned to have first light in late 2028 and to really do science observations in 2029. So 5 years. And now the students we are coming in for PhD, it'll just have first light by the time they are done. And so it's a really exciting moment. Sorry, here's Hubble. Looks like a little dot here, doesn't it? But this is the James Webb Telescope. Now look at these other comparisons. James Webb is no tiny thing. It is really in the mix for the large size. And because it's in space, it has extraordinary sensitivity. But having this ELT at 39 meters will be an incredible complement to that. Why? Well, I mentioned before, this background is a real limitation in sensitivity in the infrared. However, equally important perhaps is the fineness of detail that one can take in images with a telescope, and that scales as the size of the diameter. So this telescope will have 6 to 7 times the fineness of detail in imaging quality as the James Webb Space Telescope. And this will enable us for the first time, we think, to take pictures, resolving them from their host star of a dot, which is an Earth-like planet around the nearest 5 stars. It will have the sensitivity and the angular resolution to do that. So James Webb has sensitivity, field of view, and access to wavelengths we cannot do from the ground. The ELT has resolution, both in wavelengths, because we can build giant spectrographs that have extremely high precision in their wavelength fineness, but also fineness of detail in imaging. Spatial resolution will be exquisite. So they're extremely complementary, these two things taken together. We are very lucky at the University of Michigan to be part of the ELT family. We are members of 4 instrument building teams. We are very, very grateful for that. And in America, at universities, American football is very important. So this is a picture of our football stadium. It's the largest in the United States. It holds 100,000 people for a game. Can you imagine going to see an American football game with 99,999 friends? Anyway, that's the size of the stadium. And so when we try to explain to our rector and to the president of the university what this is all about, it's very helpful to have a picture of the ELT next to this gigantic football stadium so that they can understand how powerful and huge and big scale it will be. Well, that is really the end of my story today. It's a story of origins, about how stars form, about how planets form, and the early ingredients of life, how they're delivered from the gas of clouds and dust in space, from which stars come, into disks of gas and dust around those stars from which planets come. And it's really alchemy that we've come to. How do we create the collection of molecules and atoms from these clouds into a planet like Earth with the richness of chemical diversity and life that we have on this incredible planet? James Webb is really helping us make major progress in many of these areas, and there is so much more to come. I can't even begin to imagine what the discoveries will be. Happy if you can learn more from either the NASA website or the ISSI website, and I would be very happy to take any of your questions. Thank you very much.
I'm sure there are plenty of questions. Yes, in the front.
Couldn't these ocean worlds have black smokers, for instance?
It's a great question, and I believe the answer is yes, although I'm not an expert in this field. There can be life, of course, around these. So the black smokers are vents at the bottom of the ocean where heat from below is expelled, and it's an energy source. There's a metabolism that can occur around it. I have a hard time imagining the origin, the biochemical origin of life. This collection of the very first metabolic sequence and genetic material in a cell membrane. Once we have it on the surface, it goes everywhere. Thomas mentioned this earlier today, and I do find it remarkable. In every place on Earth you can imagine, the most inhospitable, life persists. But I don't think it can start anywhere. I think it needs maybe more special conditions. There are deep gold mines in South Africa where no photons have ever been. There's life down there. In Antarctica, where it's freezing cold, we heard today, if you warm something up to room temperature, there's nothing, it's dead. But if you hover near the ice point at 4 degrees Celsius, there is life there. And as you pointed out, at this very hot smoker vents at the bottom of the Earth's ocean, there is life. But I wonder that it could originate there. I have questions.
And in the front.
In the slide where you showed water abundance in atmospheres of exoplanets, there were two spectra superimposed, one spectrum superimposed on another. One is in gray. Yeah, the previous one. Yeah.
Yeah, this
one. Yeah, so what are the different spectra?
So the white one is one object, and it is then shown in gray underneath the other two for comparison. The blue cyan color is a different object, which seems to have a dust-rich disk around that atmosphere that is creating this excess emission in the infrared and stopping you from seeing the absorption of the molecules in the atmosphere. And the red one is from our group, and this one was from the whole community's group. And our point is that the red one and the white one, now shown in gray, these are extremely similar. So they look like the same composition, the same temperature, and the same surface gravity, which is another parameter we use to measure these spectra.
More questions? Please.
Just going back to the question about the water worlds. When we observe these planets, we're looking at one particular time in their evolution. So it could be that earlier in the evolution, there was this boundary that's needed for life.
That's an excellent point. I can't say. All I know is that it's a water world now, and we can try to create models of evolution going back, but you're absolutely right. I can't discount that. We think of many ways in which the atmospheres can be created. There is a primordial atmosphere that can form when the planet is formed. Another part of planet formation theory is that of giant impacts. And you may know that our own moon was created from such a giant impact, a Mars-sized body slamming, in fact, Willie Benz, who was here, was one of the originators of that theory. That can probably drive off the primordial atmosphere. And then there's a lot of work undergoing to think of how much volatile material, and when I say volatile, I mean like a chemist, carbon, nitrogen, and oxygen, is trapped in the mantle, and then it outgasses to create a secondary atmosphere. So all of these things are possible, and I completely agree with you. Maybe that steam world would have that possibility of having had life generated earlier when there was a crust, and then more water was delivered later, and it was drowned in a way. If we found a signature in the spectrum that we couldn't explain any other way, maybe I would resort to that. But at the moment, I think there are many other hypotheses that are less complex in a way that can be used to describe the data. But I cannot rule out what you suggest.
Going on with water-world questions, do we have an idea about the depth of the ocean? Is it kilometers? Is it down to the core? Probably not. So what's in the core? Is it rocky? Is it iron?
Yes, generally there would be a terrestrial-like composition. They're mostly silicate materials, so silicon and oxygen would be a main, like in our planet. And of course we also have heavier elements like iron. Some of you know there's debate about what the other light element could be in the Earth's core. So there's a mix of things inside, but indeed the outer part would probably have the ocean, and then we are only seeing the atmosphere and trying to infer the properties underneath.
So it could be just a shallow sea, 100 meters.
I can't say for this paper exactly what the constraint was on the mass fraction. So in these particular objects, what we have is the radius from the transit observations and the mass from measuring its dynamical perturbation on the star. If you have a mass and a radius, you can form the density. And we have the bulk density, which is a constraint on the global composition. Unfortunately, there are an infinite number of mixtures that can inform a single bulk composition. So having some constraint like this from the atmosphere we can analyze spectroscopically is very, very helpful. But the bulk composition would address your question. Water density is if it was 100% water. So we plot those tracks, but none of us think a planet would actually be 100% water. It's very difficult to imagine.
Further questions, please. Yes?
Yes. If I look for life, I could turn around the question. I don't look for an existing life, but I look for a senior life. Just take a senior habitable planet, and if you have the patterns, maybe you can analyze the situation in which this planet has been built up and how it has been living. Is this possible?
We are not at the stage where our planet formation theory is so sophisticated that we can deconstruct a unique history for the kinds of planets that we see that are mature. Most of the planets we study are around stars the age of the sun, several billion years. And all we can get are the mean density and some atmospheric characterizations of it, and context. We know the star, we know its environment, we know how far away the planet is from the star, and we know what other planets exist in the system. All of this is vital information. In some cases, you will have maybe 4 planets in a system, and you might have mean densities for all 4. Then you might start to ask yourself more complicated questions about the formation history of the 4 and how that would inform your guess at the bulk composition. But at the moment, and I look at Christoph and Jan who make these models, we don't have a unique reconstructed history from the first tens of millions to 100 million years of formation all the way to the billions. What we try to do is make demographic or census type arguments of the population as a whole. If the distribution of planets in a diagram like this, it has spaces where there are more and spaces where there are less. So our global physical model can't reproduce the details of one, but the distribution of the whole.
Maybe if I add, we don't even have it for the solar system.
Good point.
Any more questions, please? Okay, maybe I will also ask one. You mentioned these different bulk compositions of these brown dwarfs in which galaxy was in?
I only referred to the bulk heavy element abundance of the Small Magellanic Cloud
Okay.
versus the bulk heavy element abundance of the Milky Way.
Yes.
And eventually, we should get spectra of these things.
Hopefully.
Hopefully, you will get time in the Cycle 4 proposals we just submitted a few weeks ago. And then we can see what are the differences for a given temperature, which molecules are favored at a low metallicity. So astronomers call everything heavier than helium a metal, which if you're a chemist and know is ridiculous. That's not how metals are defined. But this nearby satellite tiny galaxy has a low abundance of heavy elements, and the Milky Way is kind of our reference. And so maybe the atmospheres of these will be different.
I also ask because, you know, this limit for deuterium burning is also a function of metallicity.
Yeah.
And it would be interesting. I just wonder if you would have a signal in the different luminosity distribution or something like that.
You absolutely should. However, you know, we have to then really arm wrestle, you and I, because a lot of the cooling is related to dust. And so it really may be a dust opacity thing. You may remember the old work of Richard Larson about this opacity limit related to the dust abundance, which also changes with metallicity as well. I am obsessed with this topic, in fact, and there's another puzzle, which I'll mention briefly, is that we have learned in galaxies that are way, way, way bigger than the Milky Way, so-called giant elliptical galaxies. They appear to have way, way, way more brown dwarfs and a very steep mass function in their cores, which could be a real hint to a different kind of star formation. And I would be very interested to find brown dwarfs in those objects in the low metallicity regions in the Milky Way and compare the three. It'd be very exciting to see that opacity limit change. Globular clusters are another place to try this experiment. When we started our GTO program, we dreamed that we would have thousands of hours, and we had 12 globular clusters and 15 star-forming regions and all this stuff. And then it turned out we learned how efficient the observatory is. It is not low efficiency, it's very high. But, you know, it takes time to point to a new object, and it takes time to move the filter wheels and all of these things. So we had to cut all of our programs back. Oh, and I should mention our chief, Marcia Ricci at the University of Arizona, gave 450 hours to the extragalactic high redshift team. Fascinating work, but it cut us all back considerably. Exoplanets and high redshift galaxies, that's what rules in the field right now with James Webb.
I think we had a wonderful evening, which is not yet over, because we can go to the apéro. I think there will be more time, maybe to...
Absolutely. After a glass of wine, you might get me to say what I really think.